Hello everyone, we're back again. So hopefully you're okay with grams to moles, moles to number of things. That's important because moles, as we mentioned in the last couple of videos, the mole concept is probably the most important concept in chemistry. Okay, now why is that? The bottom line is moles gives you so many important things as applications, okay? So we'll look at probably 4 different applications for using mole math, but that's by no means all of them, okay? So pretty much every calculation in chemistry will feature the mole at some point, okay? So we're going to do just 4 very popular applications, okay? Now, the first one, fundamental, really. I mean, formulas. How do we know the formula of hydrogen peroxide is H2O2? Because we can do a little bit of math that involves moles. Okay, so molecular formula H2O2. Now that's the actual number and type of atoms in a formula. Okay, if I was to draw a picture of that, it's an H stuck to an O, stuck to an O, stuck to an H. That's a kind of a geographical map, if you like. It's called a structural formula. That's what the molecule actually looks like in real life. But remember, when we name these things, whoever's left in the periodic table first, whoever's more right second. So number and type of atoms is the same. It's just we write it in that format. Okay, so hydrogen peroxide, or if you want to give it its correct name, dihydrogen dioxide, has that molecular formula. The number and type of atoms in the molecule is the molecular formula. But that's not what we find out with our math, okay? We can work towards that, but what we actually find out with our math is what's called the empirical formula, okay? So the empirical formula is the lowest whole number ratio of the atoms in the formula. So if you think about it, 2 H's, 2 O's, the empirical is 1 to 1. You can just divide that whole thing 3 by 2 to get a lower ratio. And that's exactly what we do to get empirical formulas. It's the lowest whole number ratio. Okay, now, as I mentioned, or I don't think I did, the empirical formula we can get from this math, okay? And then we can convert it just by multiplying by, in this case, 2 to the molecular formula. So we'll find this one using the mole math, and then we'll just convert to the thing we really need by just multiplying 3 by a constant. Okay, now, let's first get to grips with this whole molecular formula, empirical formula thing. Okay, let's do the first one together, then you guys can fill out the rest. Remember, just press pause, all that business, right? So remember, we can do names to formulas. Dinitrogen tetroxide. So N2 dinitrogen tetroxide. Tet is 4O4. So N2O4. What's the lowest ratio? Well, I can divide both by 2 to get 1 to 2 and O2. All right. So again, give it a pause, just work these through, and then come back and check. Okay. All right, this is a super interesting molecule. It's actually super symmetric. It has 6-fold symmetry, so it actually reduces to CH. Interesting, you can divide by 6. That's very rare, and oftentimes we'll multiply and divide by 2 for these formula interconversions, but that one's a 6, that's a rare one. Okay, here, oh, it's the 2 thing again, C2H5. And finally, P4O10 now, divided by 2, P2O5. That formula we saw before, and we've done it for molecular weight and things like that, that's not a real molecule, it turns out. P4O10 is the real molecule. Tetraphosphorus, DEC is 10, decoxide. But P2O5, diphosphorus pentoxide, is one we use all the time. But really, it's this. Okay, so empirical formula, molecular formula. Now this only applies to molecules, okay? Any molecules can have empirical formulas because, if you remember, an ionic formula is by default written in the lowest ratio. So we write NaCl, even though a piece of table salt might have Na, 6 times 10 to the 23, Cl, 6 times 10 to the 23, atoms of each type, right? It's a 1 to 1 ratio, right? So this might be a big old rock, that's the actual numbers inside, but their ratio is 1 to 1. So we always write in ionic formulas, naturally make the charges cancel if you remember that math. When you do that math, you make the charges add up to 0, you get the empirical formula. So all ionic compounds are already in their empirical formula form, okay? So this only really applies the empirical formula calculation between molecular formulas and empirical formulas for molecules. Okay. So, worked example. Now remember, chemistry is cumulative, so we're going to nip back and take a few concepts from before. Okay. So here's a great worked example. So 1.271 grams of aluminum is allowed to react with chlorine. So it's a reaction between aluminum and chlorine, essentially burning aluminum and chlorine. Okay, and we make 6.280 grams of some product. Okay, now remember the conservation of mass law. Okay, so because we have grams, we can work out moles. And the trick is, hey, because the ratio of the atoms is a whole number ratio, so will be the ratio of the moles. It will be that same ratio. So we work out the moles of each type of atom, find that ratio, and that'll be the same as the empirical formula. So that's the trick. We work out moles, find their ratios. Now, if you remember, for conservation of mass, it's just like that very first example we did with balancing, okay? So we don't know the formula of the product, so I'm not writing numbers in here because we've got to find those out, x and y, we need to figure out, right? But we can figure out, this is an unbalanced equation, right? We can figure out how many grams of chlorine we use, okay? So 1.271 plus some chlorine weighs, at the end of the day, 6.280. Do the math, 6.280 minus 1.271, you should get 5.009. So conservation of mass law there, right? Mass of reactants equals mass of product. Fair enough. Now, why is that important? Because we have the masses of the two atom types, okay? So if you look in your periodic table and look at the aluminum box, okay, you'll see that aluminum, 26.98. That's its mass number, right? So 1 mole of aluminum is 26.98 grams. And chlorine, if you look at that box, 35.45. Okay. Remember, those are conversion factors. 1 mole is 26.98 grams, 1 mole is 35.54. So we can just do the conversion right here and find out how many moles. So I'll do it as a straight conversion here, and I'll show you that trick with the shortcut. Okay, so moles of aluminum. Okay, so I'm going to find out moles equals, well, what have I got? I'm going to do grams, 1.271 grams times 26.98 grams from the periodic table is 1 mole. Grams, and I get 0.04711 moles aluminum. Leave all the sig figs because we want to see how that works later. Okay. Now, if you remember, real quick, and maybe I'll write it up here on the side, what works for atoms works for molecules as well. So molecular weight or atomic mass from the periodic table is grams per mole. Remember my trick with the triangle? Cover up the thing you want to find. So moles is grams divided by molecular weight, right? Or moles is grams, 1.271 grams divided by molecular weight, or in this case, atomic mass. It's exactly the same math, you know, something times 1 divided by the something, it's just the something divided by the something. Alright, so either way works. Remember to leave the units in, they'll cancel to give you the one you want. That's just a shortcut. And we'll use that more and more as we go through the packet. But again, you can use the formal conversion, or just cover up the thing you want, grams divided by molecular weight, or grams divided by atomic mass in the periodic table for atoms is moles. Alright, so pause there. Give it a go for chlorine, and then press play again, and you'll see what I did. Okay, so chlorine, that's still in the new way, right? So I've got 5.009 grams divided by 35.45 grams per mole equals 0.1413 moles chlorine. Okay, fair enough. So that is the empirical formula, 0.04711 to a ratio of 0.1413 moles. It's the right ratio, but it's not whole numbers yet. So the trick is, how do we make this now into a whole number ratio? Let's flip over. So what I like to do is do a pseudo formula. Okay, the great thing about a piece of paper is I'll bring it back. Okay, so I'm just going to write in the actual number of moles, right? So this number and this number, I'll just write down here, right? So that's 0.04711, and this is 0.1413. That is the actual ratio of those two numbers of moles. It's not a whole number ratio yet, but we can do that math in a second, okay? So I call that a pseudo formula. It thinks it's a formula, right? So here's the trick. Now, how do we get these into whole numbers? Okay, I'll tell you one of my favorite tricks. Well, that's actually not really my favorite trick. It's a trick of physics, okay? And in physics, they love to turn things into the number 1. So how can you turn any number into the number 1? It's an interesting question, right? Well, the bottom line is you just divide by itself. So 1,000,000 divided by 1,000,000 is 1. 5 divided by 5 is 1. Okay. So what we can do, as long as we divide by the same number each time, it will stay in ratio. And if we divide by one of these numbers, one of them will turn into 1, and one of them hopefully will turn into an integer, a number that's a whole number. Right? Now we've got to be careful. Right? We've got to be careful. Which number do we divide both by? Well, we want 1 and a number bigger than 1, right? So the trick is to divide by the smallest number. That's the trick. Because if you divide by the smallest number, which is 0.04711, this will turn into 1, same number. Now just do it when you calculate. Just pause real quick. What is 0.1413 divided by 0.04711? It's actually 3, isn't it? Ah, so that's your empirical formula. That was actually, if you think about it, the answer all along, because aluminum makes a +3 ion, chloride makes a -1, so I need 3 of them. Okay. Remember, empirical formulas are ionic formulas. Okay, so that's kind of, hey, if you just thought about it just for a second, you realized, hey, it's aluminum chloride -1, 3 of them to make 1 + 3. So we knew what the answer was before we started, but I just wanted to show you the technique. Okay, now when we do get onto molecules, we have to be careful because we can figure out the empirical, but that's not necessarily the same as the molecular, which we want to go to. Okay. Now remember, and this is our first example with H2O2, there's twice as many of each type of atom in the empirical as in the molecular, right? In other words, hey, twice as many atoms of the same type weighs twice as much. If we just work out the weight of this thing, 16 plus 1 is 17. And hey, work out the weight of this one, 16, 16, 32, 33, 34. Yeah, look, this is twice as heavy as this because it has twice as many of each kind of atom, okay? So the ratio is 34 over 17, which equals 2. All right, so here's the thing. This is what we'll get from the same kind of math, right, for a molecule. And then I'll give you the weight of the real molecule. Say, hey, you just worked out this weight, but the real thing weighs 34. Divide the real thing by the thing you worked out, and it will tell you how many times more atoms are inside. There's twice as many atoms because it weighs twice as much. So the ratio of the weight is the ratio of the number of atoms, if that makes sense. Normally it's 2. Okay, normally. Not always, but normally. Okay, so, you know, just a little finish off, work through the technique above, and then just multiply through by what factor you need to multiply by to get the real molecule. All right, so let's try this one. Now, this one has a few interesting tricks. This is a standard question, okay? Standard question. I love this on tests. If we look in the back of the packet, I'm sure there's one just like it, okay? So, ethylene glycol, all right? So, ethylene glycol, and this is an interesting set of numbers here, right? So, when you work in a chemistry lab, you make your new amazing molecule, right? Or you extract it typically from some exotic mixture, right? So you have this wonderful molecule, but you've got to make a formula for it. How do you do that, right? Well, you send it away for what's called percent composition analysis. So typically you'll put a little sample in the mail, physically put a little sample in the mail, and you'll send it off to a lab, usually in New Jersey, right? And it will arrive at the lab in New Jersey, and they put it through a special machine called a mass spectrometer. And what this mass spectrometer does, it takes the molecule and smashes it into its component atoms, and then just basically figures out what fraction, or as a percent, what amount of each atom type there was in your molecule. And you'll get something like that. So ethylene glycol contains 38.7% by weight. All right, so 100 grams of weight, 38.7 grams of carbon, 9.7 of hydrogen, and 51.7 6 of oxygen. These percents should add up to 100, of course. Okay, so that's important information. We're going to use this instead of weights, which I'll show you the trick in a second. Okay, so if you've got the percent masses of each atom type, you can easily work out the empirical formula. And then this mass spectrometer is kind of an interesting machine. It can also weigh molecules individually, and you can weigh the molecule which weighs 60. Okay, so that's the mass or the molecular formula weight, right? Molar mass, molecular formula weight. So we'll compare to that later. How many times bigger is this than the number we're going to figure out? Okay, now here's the thing. I can send any mass of sample I want to the nice people in New Jersey, right? I choose to send them 100 grams. If I send them 100 grams of sample through the mail, right, what does that mean? Well, what's 38.7% of 100 grams? It's 38.7 grams. Oh, that's the trick, right? So for carbon, we've got 38.7 grams. For hydrogen, 9.7 grams. And then for oxygen, 51.6 grams. So we've got our grams just in a slightly different way than we did before. Okay, so there's different ways to get the grams of each atom type. We can do like we did before, or typically we'll just play our trick, right? Assume a 100 gram sample with these percent numbers supplied. It gets easy. And then, hey, all we have to do is figure out, step 1, figure out the moles. How many moles of each atom type, their ratio is the empirical formula. So I'll do the first one traditionally. Carbon, 12.011 grams is 1 mole. 3.22 moles of carbon. Do the rest, okay, and get the moles, all right? You can pause, right, but I'll just do it real quick. You can do it the traditional way or just divide by molecular weight. That shortcut I showed you. There's hydrogen. And there is oxygen. So, just pause there, make sure you got those numbers. Grams to moles, grams to moles, grams to moles. That's an important skill. All right, so we're nearly there. Now remember, that is the correct ratio. Okay, 3.22, 9.60, 3.23. That's the right ratio. Now, unlike the previous example where it was really kind of unintuitive kind of decimal fractions, here you can kind of almost see what the ratio is. 3 to 9 to 3. Oh, it looks like 1 to 3 to 1, doesn't it? But let's confirm, right? So we're going to put in the actual numbers. This is the empirical formula, just not in a whole number ratio. There we go. Now what do? Point. Divide by the lowest number. What's the lowest number? This one. That's going to turn into number 1. Big number divided by small number turns into a number bigger than 1. There you go. Now remember, there's going to be a lot of, this is actual experimental data, right? So if it rounds out to like 0.99, it's really 1. If it rounds out to 2.99, it's really 3, isn't it? So what do we get when we divide them out? We get the empirical formula, C1, H3, O1. It's kind of what we kind of guessed, right? 3 to 9 to 3 is really 1 to 3 to 1. That's the empirical formula. Fantastic. Now the empirical formula weight, what does this empirical formula weigh? Well, carbon 112 plus 3 times 1 plus 16 equals 31 grams per mole, or AMUs per molecule. What does the molecular formula weigh? Remember they gave us that information. They told us the molecule weighed 60, right? 60 grams per mole. So the ratio equals 60 over 31, which is approximately equal to 2, right? So the real molecule is twice as heavy as the empirical. In other words, it's got twice as many atoms. So the molecular formula, hey, twice as many as everything, right? Oh, turn it up. This I'll recap because it was hidden. So the molecule, the actual molecule weighs 60. The empirical molecule weighs 31, approximately twice as big, a little bit of rounding there. Okay. So the real molecule has twice as many of each kind of atom, so it's not 1 carbon, it's, you got it, 2. It's not 3 hydrogen, it's 6. It's not 1 oxygen, it's 2. There you go. Hopefully that makes sense. Okay, that's how you work out an empirical and a molecular formula. All right. Now, I'm going to cut this video short because our next topic is probably the most important topic of this packet, okay? And it takes a little bit of time to explain. So I'm going to have it kind of in its own video, okay? So we'll come back and look at this in the next one.